Hello, my name is Jayant Verma and this is my presentation for EECS 4080 course project titled Compute Efficient Semantic Obstacle Detection for Robot Navigation. Here's the outline of this presentation, where I will begin by first describing the robot system of this project and then defining the problem we tackle and our solution approach. We shall then move on to the work we did and finally the results we got. We will conclude with a reflection on my learnings and future work. The references made throughout this presentation are compiled at the end for the viewer to see. So let's begin with the robot system of interest, the airchair. The airchair is a semi-autonomous driving wheelchair system consisting of multiple chairs operating as a convoy. The convoy is led by an on-foot human guide, which we see here is Dr. Peroni, the senior robotics engineer at Elder Lab. Each wheelchair in the convoy follows the wheelchair in front of it, and the first wheelchair following the human guide. It's important to mention that the use cases of the airchair convoy are at airports and campuses, including outdoor and indoor scenes, with an emphasis on the latter. While the hardware platform of the wheelchair includes many components for tasks such as motion planning, tracking, and other kinds of tasks, here we show only the necessary parts to accomplish obstacle detection. The hardware poses constraints that need to be addressed, such as the limited compute power of the NVIDIA Jetson nanocomputer, the need to be real-time for other parts of the airchair pipeline, and the software stack should be able to work with Luxonic's Oak D camera. The current approach to obstacle detection takes as input the depth map provided by the RGB-D camera. Using the depth map, a point cloud with a reference frame with respect to the airchair is generated. This point cloud is filtered to discard noise and points that correspond to the floor, therefore leaving only the point clusters it considers belong to obstacles. These obstacle points are then projected down to a 2D occupancy grid of discrete resolution. Each cell in this occupancy map explains whether there exists some object at that coordinate or not. This occupancy map is then converted to a proximity map by passing it through a proximity transform. The proximity map is normalized between 0 and 1 and explains how close a cell is to an obstacle. A cell with a value of 1 implies that the selected cell contains the obstacle, and 0 implies that the obstacle is as far as conceivable by the system. A major problem of this approach is that it uses a heuristics-based filter, and that it takes into account only depth values. There could be a fault in the contextual cases of the heuristics judgment, for example, height thresholds, cluster size, or density. Since this approach relies solely on depth values, its judgments are also very sensitive to its input. Consider, for example, the case where in the depth map of this RGB image, it identified false obstacles where there weren't any due to incorrect depth map values as seen in the circle. Furthermore, note that while there exist these benches to the left side of Dr. Peroni, they are missing in the depth map, leading to missing detections of obstacles that actually exist. For these drawbacks and the problem defined, we now present the semantic-based approach we implement in this project. Given an RGB image and its corresponding depth map, we parse the RGB into a semantic map of various classes such as person, floor, and others. We input the depth map and the semantic map into an annotated point cloud generator to tailor a point cloud with the combined annotations of depth and the class the points belong to. This is then filtered based on a combination of these annotations to result in point cloud clusters that paint a more accurate and a more robust obstacle detection compared to the heuristics-based filtering we saw previously. With the introduction of the problem and project plan ready, let us move on to the work I did. We began with the literature survey of state-of-the-art deep neural net segmentation models and recent data sets that would address the constraints put by the hardware and would perform best for the use cases of the airchair. Hence, the criteria for models was a need to be lightweight, and have a reference implementation for convenience under the time constraints of the semester. In order to have a more complete per pixel understanding of the scenes, we prioritize models that perform panoptic segmentation over instance segmentation and the least to those that just perform semantic segmentation. Similarly, to respect the use cases of the air chair, the criteria of choosing datasets include in having both indoor and outdoor scenes with a priority for indoor scenes. The outdoor scenes should include roads because the chair can be used to transport people to and from the plane in airports. Crowded scenes was also considered a plus in the selection. Furthermore, the dataset's segmentation annotations should be capable of being subsumed into the set of relevant classes that include floor, person, obstacle, and wall to support the entire air-chair pipeline. And finally, the dataset should have navigable scenes. With such a measure of selection, we collected these possible models to work with. Here, the FPS stands for frames per second, and the TOPS stands for trillion of operations per second. After a thorough analysis, we chose YOLO 11N, which stands for YOLO 11 Nano, to train on the datasets we selected. We chose YOLO 11N because it is the state-of-the-art model for object detection and instance segmentation. The device it has been tested on is the OAK-D camera, which is exactly what we're using. Furthermore, the reference implementation has wonderful documentation, and it works very well with custom datasets. It's incredibly convenient to integrate into the existing software stack of the airchair with no disruption to the person tracking task of the airchair. We chose YOLO 11N for all these reasons. Additionally, because we wanted to conduct a fun experiment, which I will define in the next slide, this experiment became possible because YOLO 11N is pre-trained on the COCO dataset. Previously, we mentioned the criteria for choosing a dataset. We analyzed these datasets under the lens of that criteria and decided to work with SceneParse 150 and COCO Panoptic. COCO Panoptic is similar but not the same version of COCO dataset that YOLO 11N has been pre-trained on. We chose SceneParse 150 because it was meticulously and manually annotated. Kindly note that it is a subset of the ADE20K dataset focusing on indoor scenes. The fun experiment is to see which of these two datasets would perform better on YOLO 11N. You can notice a stark difference in the size of the data between the two datasets, with COCO Panoptic being nearly 6 times larger than its competitor. So will the smaller, very well annotated dataset beat the larger dataset, whose cousin was pre-trained on this model? We shall see this in the results. After having selected the datasets and the model, I began with preparing the datasets, where I collapsed the classes of each dataset into the 4 relevant classes, these being floor, wall, person, and obstacle. These modified datasets were converted to fit the YOLO 11 format. With the datasets ready, I fine-tuned the model on both the datasets and also tuned the hyperparameters to see what dataset model configuration works best. With the training results ready, we did post-processing such as converting it to OAK-D blob format to fit the Luxonics camera's requirements. Additional host-side processing was such as null maximum suppression was also done, and by rewriting some code in C++ in the robot operating system, we optimized the training result to compute in real time, therefore respecting all constraints that were mentioned in the beginning. I would like to acknowledge Dr. Peroni's help throughout this section. The scripts he provided were absolutely incredible and taught me how to write a more readable code. Finally, we now get to the results. Here's a demonstration of the YOLO 11 Nano's real-time instance segmentation on the SceneParse 150 dataset. Before we begin, we can qualitatively see how well the model is able to distinguish the black coat in the background on the hanger apart from the wall. There's Dr. Peroni at the front, Mohammed, a master's student, on the right, and then me, waiting to test the model from afar. We can see how the model segments out the wall in red, obstacles in blue, floor in green, and people in purple. The segmentation is in real time at 18 frames per second. We experimented with the following hyperparameters to see what configuration of the model works best. Kindly note the motivation to freeze the initial layers was to test how well the model can perform by relying on its pre-training. Since feature extraction occurs in the initial layers, we want to see if we can bypass that by reusing what it had learned during its pre-training. Because freezing versus not freezing the layers had the most interesting results, we shall discuss them here. The training results of SceneParse 150 shown here when trained without freezing the layers had a steady loss decline in all the kinds of losses including segmentation, classification and box loss between the training and the validation set, meaning that there was no overfitting in the case here. The metric results for validation set also increased as the number of epochs grew, eventually converging after a certain point. The precision grew very well, and so did the recall. When we froze the layers, we still saw a drop in the bounding box loss and the classification loss among the training and validation set. However, this was completely opposite when we saw the difference in the training and the validation set for the segmentation loss, which in fact grew as the number of epochs went up, meaning that there was overfitting happening. We also saw failures in the validation set when ran on the metric results. For example, the masks for precision dropped as the number of epochs grew, and so did the recall. Here we see that once the loss had converged in the case of frozen layers, while the box loss is about the same for the training and validation set, and same goes for the classification loss, the segmentation loss is incredibly poor, where it actually increased instead of decreasing. And the metrics were also had poor performance for the validation set values, where precision and recall were incredibly low. In the case of not freezing the layers, the box loss, segmentation loss, and the classification loss were right about the same between the training and validation sets. The performance in metrics was also a lot better than the case of with frozen layers, with the precision being very decently good. However, the recall could do better. The Coco panoptic results were very interesting, where when we froze the layers, the loss curves for the box and classification dropped in between both the training and the validation set. The segmentation and masks loss was terrible as it increased as the number of epochs grew. In the case of validation set metric results, the precision dropped as the number of epochs grew, and so did the recall for the masks. Well, you may be wondering that we saw such a pattern of overfitting when we froze the layers for SceneParse 150, but and we had good results when we did not freeze the layers for SceneParse 150. However, in this case, we still see that there is signs of overfitting in the case of segmentation loss as the model's epochs grew, and the precision and recall both drop as the epochs grew. This was very surprising. Since the training results of the COCO panoptic dataset proved to be of little use, we can conclude that SceneParse 150 is the winner. Very surprising. Now, we shall conclude this presentation with a reflection of my time at Elder Lab. I learned a lot. I read about 18 papers, and while we had a very ambitious goal at the start of trying to figure out the whole implementation pipeline for semantic segmentation, we managed to complete a big chunk of it. I learned how to prepare and fine-tune models, and I had a lot of fun doing this project. I am very excited for grad school right now. I would like to acknowledge Professor Elder for this opportunity and Dr. Peroni for his help throughout this project. And also I had fun discussing things with the graduate students. Now for the future work, we need to create a semantic filter and an annotated point cloud generator in order to finish the semantic obstacle detector pipeline and also figure out ways to improve the model recall. Thank you.